In this section, we'll talk about how to write complex numbers in polar form. So what we've seen so far is a complex number written in rectangular form. Now, what we saw was z equals a plus bi, but the a and the b are just placeholders. And so in this image, we see that complex number written as z equals x plus yi. That's just another way of writing it. I could write z equals, c plus di. They're just placeholders. Writing it as x plus yi, however, is really nice because we're used to x's and y's being on a horizontal and a vertical axis. So writing x reminds us that we are on the horizontal axis, or in this case, the real axis, and writing y reminds us that we are on the vertical axis or the imaginary axis. So we know how to write a complex number in rectangular form. What does that look like in polar form? Well, from your work with polar notation, you might expect that the polar form of a complex number has something to do with r's and thetas, and you would be correct. It means that we are simply going to take z equals x plus yi, and we're going to express that location in terms of some angle, theta, and some r, which is the radius of the circle that would be inscribed if I could put a circle and have it go through the point z equals x plus yi. The r is the distance from the origin. That's why we can call it the radius. It's often referred to as the magnitude, which is going to be important in some of your later studies, or the absolute value of the complex number, where we can simply use absolute value notation and the complex number. All right, so how are we going to do this? So we're going to take the point x comma y that represents the rectangular form of a complex number where z equals x plus yi, and we're going to convert from rectangular to polar form simply by recalling some of our past knowledge of the relationship between x and y. Way back in your studies of trigonometry, you were probably taught that the cosine of some angle is equal to x over r. So if I solve that for x, then I can say that x is equal to r times the cosine of theta. And same thing for y, right? We learned that the sine of theta is equal to y over r. So solving for y, we get that y is equal to r times the sine of theta. All right, so that is what I'm going to use. By direct substitution, if I have the rectangular form, z equals x plus yi, in the place of the x, if I want to write this in polar form, then I'm going to substitute in r times the cosine of theta, because that's what x is equal to, right? And in the place of the y, I'm going to substitute in what y is equal to, which is r sine of theta. Now, the I that was listed in the rectangular form is still here in the polar form, okay? Now, that is a perfectly good representation of the polar form. However, you might notice that in each one of these terms is an r. And so one thing that we can do is we can factor that r out, and that leaves us with just cosine theta plus sine theta times I. Now, in the form that we just wrote, we had the I on the end. It's perfectly fine to leave it on the end, but a lot of times you'll see it notated with the I in front, just so that it's clear that the I is not being included in the argument of this sine function. All right, let's summarize now some of the things that we know. We know that the rectangular form of a complex number is z equals x plus yi. We know that the polar form of a complex number is z equals r times the quantity of cosine theta plus I times the sine of theta. And then we also know a bunch of relationships between x, y, r, and theta. We know that x equals r times the cosine of theta, y equals r times the sine of theta. We know x squared plus y squared equals r squared. And then we know all of these things about tangent, cosine, and sine of an angle. So we know that the tangent of an angle is equal to y over x, the cosine of theta is equal to x over r, and the sine of theta is equal to y over r. We have all of these things that we can use to help us do these conversions. So let's take a look at an example. This one asks us to express the rectangular form of the complex number z equals the square root of 3 plus I to rewrite that in polar form. Okay, so because they told us that it's in rectangular form, then we know that the square root of 3 in that first position represents my x, doesn't it? All right, so x is the square root of 3, and what's my y value? My y value is the number that is hooked onto that I. There's nothing written there, so I know that it's 1. Okay? Now, what that means is if I were to plot the rectangular form of this complex number, it would be represented by the ordered pair square root of 3, comma 1, which is in the first quadrant. All right, I like to remember that because what I'm going to do to rewrite this in polar form is I need to find out what r and theta are. So I want to find r and theta. And when I find theta, I want to make sure that that angle is also in the first quadrant. That'll be sort of my check to make sure that I've done it correctly. All right, so how do I find r and how do I find theta? If I'm given x and I'm given y, then I would say using x squared plus y squared equals r squared is the way to go. All right, so let me change colors to make this look not quite so messy. I'm going to say that x to the second power, or square root of 3 to the second power, plus y to the second power, which is 1 to the second power, is equal to r to the second power. Now, what does that equal? Well, square root of 3 squared is 3. 1 squared is 1, 3 plus 1 is 4, and the square root of 4 is 2. So that turned out nicely. My r value is 2. So let's just start doing this. I'm going to say that z in polar form, right, in polar form is some r value, which I know is 2, times the cosine. Now I've got to find out what theta is, don't I? What is theta? Well, to find theta, I can either use tangent, cosine, or sine, and any of these will work. Most books are going to tell you to use tangent, and the reason why they tell you to do that is because the y and the x have been given to you, right? So 1 over the square root of 3. If I want to use cosine, I can, but let's see, I would have square root of 3 over my r value of 2. If I've made a mistake in solving for my r value of 2, then of course I'm going to make the same mistake up here when I try to solve for theta. So I would say this: if you feel confident with your r value, you feel really sure that you've done it correctly, I personally think using cosine, or let's look at what sine would be. Sine would be simply 1 over 2. I say using cosine or sine is probably easier because my guess is that you might have those angle measures memorized. Maybe you have this one memorized as well. Do you know what angle produces a tangent that's equal to 1 over square root of 3? If you do, great. But if you don't, then use cosine and sine. What angle produces a cosine of square root of 3 over 2? Whatever that angle is, it should be the same angle that produces a sine equal to 1/2. And I believe that that angle should be, what is it? Pi over 6. Now, I like pi over 6 because it does give us that first quadrant angle, doesn't it? All right, so I think I'm just about done. All I have to do to rewrite this in polar form, I've already put in my r value. Now I'm going to put in pi over 6 plus I times the sine of pi over 6, and I'm done. I have turned I have turned, let's just see here, the rectangular form of the complex number into the polar form of a complex number. Okay, let's take a look at an example. And in this example, we're being asked to express the following complex numbers in polar form. We have z equals -3 plus 3i, z equals 3i, and z equals -4. Okay, so polar form is what we're looking for. Polar form is going to be taking a number that's in rectangular form, which gives us x and y, and rewriting it in terms of r and theta, right? Okay, so I'm just going to write this down so I remember what I'm doing. Okay, so on part A, z equals -3 plus 3i. They are giving me that x is equal to -3 and that y is equal to +3. If I were to plot this complex number, the ordered pair would be -3, 3, and that puts me in quadrant 2. All right, I'm going to make a note of that always from the very get-go, so that I make sure that I'm in the right quadrant when I solve for theta. All right, so I have x, I have y, I need to find r. Let me find r. R is going to be found by using x squared plus y squared equals r squared. So I'm going to say -3 squared plus +3 squared is equal to r squared. So that gives me 9 plus 9, which is 18. And so r is going to equal the square root of 18, which is the square root of 9 times 2, or how about we call that 3 root 2. Okay, so we have the radius, and now I need to find theta, don't I? So theta can be found by using tangent or sine or cosine. Or maybe even you just plot this point, z equals -3 plus 3i, you plot that on an xy axis. If you were to plot this on an xy axis, excuse me, not an xy axis, but a real and an imaginary axis, right? You would be sort of, your angle is going to be right in the middle of the second quadrant, isn't it? Now, you might recognize what that angle is without even doing any computations, right? Because we know that in terms of radians, right, that angle measure halfway in the second quadrant is the angle measure of 3 pi over 4. Okay, so if you see that, then go ahead and just use it. If you don't see it, then you may choose to use say tangent of theta equals your y value over your x value, so 3 over -3, which is going to provide you with theta equaling tangent inverse of -1. Now, you're going to see a tangent inverse of -1 either in the second quadrant or the fourth quadrant. If you put this into your calculator, remember, for tangent inverse, you always return out of the calculator an answer between pi over 2 and -pi over 2. So the calculator would tell you -pi over 4. But that's why we did this at the very beginning. We know -pi over 4 is not what we're looking for. We're looking for the angle in the second quadrant. So if you don't graph it and you just use your calculator, I want you to remember that you can always add the period of the function, which for the tangent is pi. If I add pi to this, now I get a theta value that is 3 pi over 4, and sure enough is in the second quadrant. So the moral of that story is go ahead and graph the point and see if you can recognize what the angle measure is. If you don't want to mess with that, then go ahead and use your trig ratios, remembering that if what the calculator gives you is not in the correct quadrant, then maybe you need to add the period to it to get an angle that is in the right quadrant. All right, so let's see here. What is my final answer? My final answer, I'll just put this in red down at the bottom. Z equals -3 plus 3i is in rectangular form. In polar form, that turns into the radius, which is 3√2, times the quantity, the cosine of 3 pi over 4, 3 pi over 4, and I think I need to erase this. Erase, can I erase all this? I hate to erase all of it, but I'm going to erase it so that I have some room to write. And go back to my red pen, plus I times the sine of also 3 pi over 4. All right, that's the polar form. All right, part B. Part B. So z equals 3i. You'll notice that there's only one term on this. Z equals 3i is equivalent to z equals 0 plus 3i. In other words, the I is the imaginary part. Because they didn't write the first term, then that means that the real part must be 0. Now, you can definitely identify that x is equal to 0 and that y is equal to 3 and that we have an ordered pair that is 0, 3, right? If we were to plot that, we'd be at 0, 3. Now, I want you to think about this. On part A, we identified the quadrant. What quadrant are we in here? Well, 0, 3 is not in a quadrant at all, is it? Let me just draw a picture. So we have our real axis and we have our imaginary axis. 0, 3 is going nowhere on the real axis and it's going up 1, 2, 3. Okay, this is what we call a purely real complex number. When there is, no, excuse me, not purely real, purely imaginary complex number. Glad I restated that. Purely imaginary. Purely imaginary. And that's because there is no real part. It is purely imaginary. Okay. Now, do I have to go through all of the arithmetic to determine what the r and the theta are? The answer is no. I can look at this thing and I can see, let me switch to black. I can see that this radius, right, is 3. And I can also see that the theta that gets me to that point is going to be pi over 2. Okay. Where you do have to do a computation is if you're not on an axis. Okay. So for this one, if I just draw a picture, then I can say that z equals 3i in polar form is equal to z equals 3 times the quantity, the cosine of pi over 2 plus I times the sine of pi over 2. I think this idea of plotting the complex numbers is really nice because it really gives you a visual, and maybe you don't need to do as much arithmetic. Showing your work can be arithmetic. It can also be drawing a graph, a photo, and or a drawing of just a sketch, and using that to convince yourself that you know or it makes sense to you. All right, part C. Let's move on to part C. And if we called part B purely imaginary, part C is purely what? We have -4, and on this one we don't even have an I, do we? So we're going to say that this one is purely real, right? There is no imaginary part. Okay, so I would say that x is equal to -4 and y is equal to 0. The ordered pair that I would plot would be -4, 0. This one is also not on or in a quadrant. It's going to lie on an axis, right? We have our real axis. We have our imaginary axis. -4, 0 is going to have us sitting 4 units to the left of the origin on the real axis, okay? So again, when we are sitting on an axis, we can do the arithmetic if we want, but we can also just identify that from the origin, this is going to be a radius of 4, isn't it? That's a radius of 4. And from the positive x-axis, what is that theta? That theta is going to be pi, isn't it? Okay, so for this one, let me just put this down below. Z equals negative z equals negative 4 can be rewritten in polar form as z equals 4 times the quantity, the cosine of pi, plus I times the sine of pi. And that's it.